Now let's move on to talking a bit about some advanced strategies. And you've already touched about a bit upon, the future of C++ and what you see coming. So let's discuss that a bit more as well. So the first question we have for you is, when should a developer consider implementing a custom allocate memory pool?
Oh, that's interesting. Well, the first thing you should do is measure what you already have and make sure it doesn't do the job for you. If you're spending time on something, it has to pay off. So if your implementation provides stuff that is sufficiently fast for your needs, put your effort to something else. We have good libraries. Now, if you realize that you have bottleneck, suppose that you're working in the finance domain and you have nanoseconds little speed constraints because you need to buy stuff fast and sell stuff fast. Let's say there's something on the stock market going on, you're stressed. That's been known to happen. Well, then sometimes, yes, you will want more control over what's going on. Maybe you don't want any allocation to occur because you just want to manage memory. So you want to use a buffer on the stack. That's a common case. We have two big allocator models in C++. The traditional one associates an allocator with a type container. So it's type-based. It's extremely efficient, but if you have many allocator types, you will end up having many container types, and sometimes it leads to code that's a bit more involved than you would like. So it's efficient, but I don't know if you redid the language, we would do it that way. But it's still something that you should know about. We have a whole chapter on that. The traditional allocator model forced you to write a lot of code on top of what you really wanted to write. That has been simplified through the efforts of mostly the Bloomberg people, I would say, in 2011. They did a lot of work on that. Now it's traits-based, so you write the same kind of thing, but if you don't provide the boilerplate code, it's done for you automatically. So if you write a function, they take yours. Otherwise, the sensible defaults are there and they're on compile time, so there's no cost to that. So again, the transition from one model to the other has been covered in the book. It was an interesting thing to write. And more recently these days, since 2017, we have the PMR model, also from Bloomberg, if I remember right, where you're value-based instead of type-based. So the PMR vectors say an additional member, which is a pointer to the allocator. So instead of being in the type, it's in the object. And then when you're allocating and deallocating, there's only three functions to write if you write your own, but it's a virtual function call. Normally, when you're calling something like malloc and you're allocating stuff, it's a costly operation to do. So the indirection of a virtual function call is not much of a cost, and that's what you end up doing in the end. So it's a very efficient model for that. If you're at the nanoseconds level, sometimes that indirection costs you too much for your needs, and you need to use the more traditional model where there's no cost, even though you write a bit more code. So, it's a balancing trade-off there that you have to do, and if you have to measure to make sure that you get the right tool for the job. So yes, if you want to use a buffer on the stack with, let's say, PMR, it's easy. There's something built in. You just say, I'm using that. Here's my buffer, and it's very easy for you as a user to do. And the small cost of virtual function call, maybe it's not much of a cost for you. Measure, it works. Problem solved, awesome. It's still not enough. You can write it yourself with a traditional model. It's going to be faster, but you're going to write a bit more code. Again, measure, and you get to do what you need to do.
Got it. And so what should developers be measuring, and what kind of measurable benefits do you think such techniques offer in the real world?
Oh, that's interesting. So it's a two-part thing. What the benefits are to really depend on your application domain. So I would say that in most cases, your main problem is the deterministic behavior of your code. So if you're doing real-time systems, you need to know what the worst-case execution time of your code is. If you're doing allocation in a general sense, that's very hard to do because the time it takes to allocate a chunk depends on the state of your memory at a given time. Where are the holes and how can you find them quickly to have a hole that's big enough for your needs and take it? So if the memory is very fragmented, you might search for a longer time, but if it's not. So the predictability of the action will be your problem there. So what you want to do normally is try to guess what the worst case will be, and not really the average case so much as the average deviation of your time, to be sure that you, between a fast one and a slow one, there's not much of a difference. You want to be predictable. If you use the default stuff, you might not get predictability because you never know what the memory will be. If you want to be predictable, you have to write it yourself because you have to know the pattern. That's why you need control over things. So what do you measure? Now, some people use allocators and other allocation devices, like you write your own new or your own delete. We do that in the book. Sometimes it's because they want to know where the memory is. They want to do tracing. They want to do logging. They want to know what's warm and what's cold in their code. So where is the action going? Why are people not going in that direction? Sometimes knowing how the memory layout is helps you figure out stuff. So sometimes you just overload the reallocation devices because you want to know what's going on. You want to trace how memory is being allocated, where it is. So that's how we're interested in something. It's from a measurement. You know the layout. Of course, you want to know, as I said, worst case, best case, maybe not average case. That's interesting in itself if you want throughput, but if you're doing real-time stuff, the worst case is your enemy. You don't want to be slower than your worst case because then you'll hurt someone or break something, and that's not good. So this is what you really want to measure. But if you need to measure it at runtime, you're already a bit in trouble because you don't really know what's going to happen. So if you want something predictable, you have to have a clearer model when you compare your stuff. What else? Yeah, okay. So the other thing is there's trade-offs. So let's say you know what your worst case scenario is in terms of how much memory you will need. Well, the way to get control over things is you allocate everything up front and then you manage it yourself. So there's no allocation costs as you're going on. You already have the memory, but of course that means you paid for that. And you have less memory left for doing something else. So sometimes it's the overall amount of memory you're consuming that you're interested in. Take a vector, for example. It's related, but not necessarily the same thing. But let's say you when you're full, you resize or you reserve, whatever. So your vector grows. Well, if you grow by a factor of 2 every time, you will grow faster, but you're generally going to be faster too when you add stuff because you will allocate less often because you grow faster. You grow by wider chunks. If you grow by 1.5 times the current capacity, you will grow more often, maybe, but you will consume less memory overall because you won't be over allocating as much. It's a trade-off. It's a trade-off as to what kind of memory do you have in your hands, how much do you have, how fast do you need things to go. So yeah. So your question was, what do I measure? These would be factors I would have in mind.
Okay, brilliant. Thanks for that. It was some really good insight.